Okay, so this is just the appendix for the video on curve fitting. Here I'm going to run through how to evaluate the derivative of the Lorentzian with respect to f0, which is what we skipped over previously. So it was in the step 1 part of the video, and based on what we needed to do was differentiate our Lorentzian, our model Lorentzian function, with respect to the parameter f0. So how do we do that? So this is our Lorentzian function, and we notice the f0 is inside of these brackets in the numerator and the denominator. So basically my approach is going to be very lazy. I'm just going to use the chain rule over and over again to brute force the answer. Some of you who are better at mathematics will be able to do this without all these steps, but for me, this is the way I'll do it. You just don't have to use your brain too much. You just have to constantly set values, set a set of variables within inside of your function equal to a parameter and apply the chain rule over and over again. You get to the right answer eventually. It's just time consuming. So let's start with the first one. So what we're going to do, we're just going to take the inside of this bracket, which is squared, and we're going to set it equal to a parameter alpha. So basically it's 2 times f minus f0 divided by delta w. And then in that case, our Lorentzian function just reduces to the following, which is r max multiplied by r0 plus alpha squared divided by 1 plus alpha squared. Okay, so what we need to do, we get alpha, and we're just going to apply the chain rule. So to do that, we're going to first of all separate out these two fractions and find the derivative of alpha with respect to f0. So in our case, so the left fraction is just a constant. We drop the f0, and the derivative of alpha with respect to f0 is negative 2 over delta w. And we'll just put that into this box here because we're going to use that later. Excuse me. Okay, so let's go back to our Lorentzian. This is what we have. We still need to simplify this a bit more if we're just going to find a simple derivative. So the next thing to do will just be to take out this squared function. So we're going to create a new parameter, call it beta, set it equal to alpha, so it's equal to alpha squared, sorry. Just to be clear, this is not the beta we used within our video to identify the parameter column vector. This is just a temporary variable for applying the chain rule. And then we see that our Lorentzian reduces to something slightly nicer, still not differentiable without a little bit of thought. So now let's once again take the derivative of beta with respect to f0, and to do that we're going to use the chain rule. So the derivative of beta with respect to f0 is equal to derivative of beta with respect to alpha multiplied by the derivative of alpha with respect to f0. So the derivative of beta with respect to alpha is of course very simple, 2 alpha, and the derivative of alpha with respect to f0 is what we calculated previously. So there we go. We can just combine these and we have our answer. So we now just need to substitute alpha back in. Alpha is equal to 2f minus f0 over delta w. Substitute that back in and we have the following. And we can now put this up into our box. There we go. Okay, so let's go back to the Lorentzian, and once again we'll try and parameterize it to make it slightly easier. And let's just do this. Let gamma equal to 1 plus beta. And then we find our Lorentzians getting slightly more simple. Okay, so we need to once again apply the chain rule. Derivative of gamma with respect to f0 is equal to the derivative of gamma with respect to beta multiplied by the derivative of beta with respect to f0. This is very straightforward. Of course, the derivative of gamma with respect to beta is just 1, and we have the derivative of beta with respect to f0 from before. So we can just evaluate this, and we find it's the same as d beta over df0. So let's just put that back into the box. Okay, one last step. We're going to take a parameter phi, and we're going to make that equal to 1 over gamma. And then our Lorentzian simplifies to something which is straightforward. It's linear in the parameters we have, so we can evaluate it reasonably straightforwardly. Okay, we apply the chain rule one last time. So in this case, the derivative of phi with respect to f naught is just equal to the derivative of phi with respect to gamma multiplied by the derivative of gamma with respect to f naught. Apologies there, that should be f naught, not a phi naught. Okay, so this is reasonably straightforward. The derivative of phi with respect to gamma is just minus 1 over gamma squared, and the derivative of gamma with respect to f naught we have previously, which is just this. Multiply them together and we get the following. So now we just need to substitute gamma back in, do a little bit of simplification. Gamma is 1 plus beta, which is 1 plus alpha squared, which is 1 plus 2 times f minus f naught in brackets divided by delta w squared. And we multiply it out and we get the following. It's a little bit messy, but that's what it is. And we can put it into our box. For the sake of fitting it within the box, we're just going to put the gamma back in, but that is the answer. Okay, so here we have our Lorentzian. Now let's just evaluate the answer. So this is our Lorentzian reduced using the parameters we have, phi and beta. We can just multiply it out to make it slightly more straightforward. So in this case we use the product rule. R max is just a constant, R0 is just a constant. So the first term we have is R max R0 d phi over df naught, and then on for the second term we have R max and multiplied by phi times beta, and both of these are functions of f naught, so we have to use the product rule. And that's hence how we get this d phi over df naught multiplied by beta plus d beta over df naught multiplied by phi. Okay, so we can now just substitute in from our box on the right hand side, and doing that we get the following. We still have our gammas here and a phi and a beta, so we just need to now substitute all of the components back in from before. Let's do a little bit of simplification, some terms we can take out the front there. And we see we just replaced our phi with 1 over gamma. Now we can take 1 over gamma out the front, leaving us with the following. So we're getting there, we still have a beta on the top and a gamma on the bottom. So we need to do a little bit more substitution. And we get the following. So that is our answer. Eventually, it's a little bit messy, but that's the way you do it. You can be a little bit quicker with less steps if you use the quotient rule, but I don't like to use the quotient rule just because it's a bit messy. I like to just use a product rule and lots of intermediate variables in the chain rule. That's the way I do it, because it's it may take a lot more time, but you're just a lot less likely to make mistakes. And if you do make mistakes, they're a lot easier to identify. So it's sort of a brute force method. I'm a physicist, and that's my approach to mathematics. Basically learn the technique and then brute force it. I don't want to have to really rely on using tricks and so on too much, because the odds are I will probably make a mistake and then find it difficult to identify it. So that's how you do it. That's how you evaluate dl over df naught. You can use a very similar technique to evaluate dl over d delta w, and then once you have these parameters evaluated, these derivatives, you can evaluate your Jacobian and carry on fitting as in the original video. Thanks so much for watching.